Hi everyone, I'm Takenobu Kiyama from University of Tsukuba. Today I'm going to present a method for completing missing 3D point cloud reconstructed from aerial multi-view images using self-attention mechanism. These days, the generation of 3D city model is attracting attention for use in the disaster simulation, drone navigation, and the other applications. Level of detail (LOD) of 3D city model are defined by CityZML and are classified into 4 levels. As shown in the figure on the right, LOD1 is a model consisting only of the area and the height of buildings, while LOD4 is a model with information on the side and the interior of buildings. For extending the application, city modeling with more detailed object is preferred. However, the majority of existing city model consists of LOD1 and 2, and there is a demand for city model with more detailed representation such as LOD3. Although there are existing methods to generate LOD3 models, such as using onboard LiDAR. These kind of methods are not easy to use because they're not only expensive but also the area that can be covered by a single measurement is limited. Therefore, we consider that there's 3D point cloud with site information should be generated using only aerial multi-view images. With the development of drone technology, anyone can easily acquire aerial images, and by applying 3D photogrammetry, such as structure for motion, to these images, 3D information on the terrain can be reconstructed. This is not only make it less expensive than LiDAR-based measurements, but also enable us to measure a large area at once. On the other hand, when reconstructing 3D images, from such aerial images, it is difficult to fly and shoot at a low altitude because of privacy protection. When the drone shot a structure with an overhang at the top, the drone camera cannot capture the side and result in the occlusion as shown in the left. Using such an image for 3D reconstruction, the point cloud is missing in the area under the eaves, and making it difficult to obtain the accurate 3D information as shown in the figure on the right. Thus, in this research, we developed a method to reshape the point cloud by adding new prediction points to reconstructed point cloud. As shown in the left figure, the building point cloud reconstructed from aerial images has a deficit at the eaves, and such a point cloud is used as our input for this method. The final output will be building point cloud with a missing part complemented. Here is an overview of the proposal method. In this research, we utilize a supervised learning with self-attention. 2 sets of training data are given. One is a point cloud containing the missing point generated by SFM, and the second one is a point cloud that is as ground truth without any missing part. The network is trained so that a point cloud with a reasonable shape can be added to missing points. Since it is difficult to measure and create a dataset of exact 3D shape of the real building, a synthetic 3D CZ model is used to generate the training data, as shown in the upper part of the figure. In the prediction phase, in the figure below, Missing point cloud is generated from the actual aerial images and used as an input to the network. The trained network is complete the point cloud by adding a reasonable shape of point to the missing area. Okay, let me first talk about how to create a missing data with SFM. As I mentioned, a Shiji model is used to generate the training data. Shown in the left figure, a virtual camera is placed in the upper part of the space to imitate the drone shot. By acquiring a rendered image from this virtual camera and applying SFM, missing point cloud is generated, and as shown in the lower right figure. We can see there are some missing part under the eaves, like here. Next, let me talk about generation of the point cloud that will be the ground truth. To generate a ground truth, surface sampling of the CZ model is performed. Attach the triangular mesh to the 3D CZ model of the building used earlier, and perform the point sampling on each mesh surfaces. Since the CZ model includes an item with internal structure, such as stairs and the floor surfaces, the point cloud might exist inside as well. The point cloud reconstructed SFM is only the outer surface, so only the sampling the surface from the mesh is not appropriate to the ground truth point cloud. Thus, we conduct the direct visibility of point sets to remove the inside point cloud. Direct visibility of point set is a method of taking the point cloud from the specified viewpoint and extract only those point clouds that can be judged as outer surface. Showing the lower left figure, viewpoints are set to surround the point cloud, and the direct visibility of point set is applied at each viewpoint to generate the external point cloud. Next, I would like to talk about network training. The number of the point clouds that can be generated depends on the amount of the original CZ model. However, since it is quite difficult to collect a large amount of building CZ data, the network is pre-trained by ShapeNet, which is a large dataset of CZ model. The network is pre-trained by generating a point cloud from various categories of CZ model in the ShapeNet, and the fine-tuning is performed using the pre-trained parameters. This ensures complementary accuracy even when training on the small amount of the dataset. Next, I'll talk about the structure of the point completion network. As mentioned in the introduction, we will use a self-attention mechanism for the network. We utilize a method called pointer, which employed the transform architecture. The network takes a missing point as an input, acquire the local feature using DZCNN, and adds the local feature to local information to each feature using MLP, and converted point cloud into feature series data. Then, by inputting the series data into the transform architecture, the entire feature is acquired, and then the data is formed by MLP, and MLP to output the completed sparse point cloud. Based on this sparse point cloud, upsampling of the point cloud using folding net produce the final dense complementary point cloud. Thus, the loss function calculates the geometrical similarity by comparing the chamfer distance to the ground truth point cloud for both the sparse point cloud, and the output dense point cloud. Finally, I talk about the prediction result on the real-world data. In order to measure the utility of the method for real-world data, SFM is applied to aerial images taken by drone, and point completion is performed on the reconstructed point cloud. We shoot the drone images from the altitude of our 100 meter and adapt SFM to the obtained images to generate a terrain point cloud as shown in the figure on the right. By extracting a building area from the obtained point cloud, a missing point cloud is generated and input to the trained network. Since point cloud reconstructed from real-world data vary in the number of the points and the scale, we added pre-processing such as rescaling and adjusting number of the point to input point cloud completion work. This is a result of the point completion on the real-world data. The left side of the figure shows the missing point cloud from the input SFM data, and the right side shows the point cloud that was completed. You can see that a point cloud with reasonable shape was completed for the missing part, such as under the eaves. Whereas, as shown in the bottom example of the result, there are cases where large missing area close to ground were not completed well. We believe this is due to the universality of the shape under the eaves. In contrast to the unique characteristic of each structure in the area close to ground, such as entrance and porch. In order to solve this problem, it is considered necessary to expand and diversify the training data. Since the training data used in this study was small, compared to the large data set like ShapeNet, we consider that further data expansion will enable prediction of reasonable shapes. To sum up, in this study we have produced a method for completing a missing point graph reconstructed from aerial images. A transformer-based network was used for a point cloud completion and for training. Pre-trained a large dataset and the building point cloud created in the virtual space were used. The prediction on the real-world data showed that point cloud with reasonable shape was completed in the missing area. We believe that expansion and diversification of training data is necessary to improve the accuracy. That's all. Thank you for your attention.